Hello, everyone. Welcome back to the Exception Handler. Today, we'll crack open a system design concept that felt like a boss to me: consistent hashing. Sounds scary, right? It's the backbone system for Redis, Memcached, or even DynamoDB. And if you've ever wondered how these beast systems stores or retrieve these large amount of keys across their different servers, you are at the right place. So before we start, grab a coffee or Red Bull and let's start. So as you all know that system design is all about trade-off. Now, before we understand consistent hashing, I would want to discuss an alternate approach that came to my mind so that we can start building on what the problem this approach had and how does that get solved with consistent hashing. You all know that one trick that we have learned when we were first building our distributed cache. Yes, take the key to the modulus with number of servers that we have, and boom, you get the exact index of the server where the key has to reside. Simple maths. Feels genius, right? Let's say we have 10 keys starting from 1 to 10, and we have three servers to distribute these keys, right? Let's plug this formula and see how these keys are distributed nicely. So from this diagram, you can understand that I have distributed keys starting from 1 to 10 within three servers. Everything is clear. It's working. Life is good. You have delivered this piece of code successfully on your production. Until someone, probably your product manager, decides to scale the system up and add another server. Now what? Because of adding another fourth server, guess what will happen? All the keys will break. Let me show you how. Now, from this diagram, you know that the formula has already changed, right? Earlier, you were using percentage 3 versus now you have to use percentage 4. So that means you have to do remapping of all the keys in the system and align them to the four servers. So now, maybe this isn't a scalable distributed approach, right? So I did what any sensible developer would do in this situation. I Googled it. And I found and very interesting thing. What I found was a bizarre concept called hashing. And I promise, once you get it, it will feel like you have unlocked another level of system design. So let's walk into the ring. Okay, so by now we both have realized that the modulus logic that we were using is kind of trash when we are scaling the system, right? But every breakdown needs a breakthrough. So that's when I met the real MVP of this entire system, the hash function. Now, if you're like me, whenever you hear this word for the first time, hash, you either think about your morning breakfast potatoes, or you are thinking about the cryptography which you pretend you understand while you are in an interview. But in our context, a hash function is that magical math spell which takes in an key and gives you a number that is of a fixed size. For example, if you get a key user 123, it would emit out a fixed number every time when you call this hash function. Pretty cool, right? Now, that's when the actual drama begins. Any hash function that can be used in your caching server has to have few properties. First property is it has to be deterministic. That means every time you pass the same key, it has to emit the same hashed value, right? Then your hashing function should be fast enough. No one wants to wait for 100 milliseconds to get that hash value out, right? Then all the hashing values that can be emitted out should have equal likelihood to get as an output, right? So that you don't have a cluttered space over on single section of your numbers that are your output from the hash function. And yes, there are a lot of hash functions out there. MD5, SHA1, SHA256, and you probably have used them in a lot of spaces, for example, your password storage space. Hash functions are the same hash functions that you would use for balancing your API servers. You can also use for protecting your password against that intern that still uses password 123. Hashing is everywhere. You would have seen hashing in your Git commits. You would have seen them in sharding your database. You would also have seen them in load balancing. But we barely notice them until and unless something breaks on your server, right? When you combine a good hashing function with a magical thing that is hash ring, that's when the real magic begins. If you stay around for next 120 seconds, that will change how you think about scaling a system forever. I know you guys have the same question that I had when I first heard the word hash ring. I thought that this is some kind of cryptic DevOps shortcuts. But stay with me, this is very important concept which will unlock the new levels of your system design and give you a new level in understanding how distributed systems are designed. So here is the deal. Imagine that you have a giant ring, not your wedding ring, but think about this as more of as a circular number line. Let let's say it has 2 to the power 32 numbers. No one is going to count, but imagine that this is an imaginary ring that contains 2 to the power 32 numbers, right? Now, use any hash function that you want. For example, let's say I want to use SHA-1. And now you will have to pass the server identifiers of the servers that you have all together to serve for your distributed cache. For example, let's say you have servers with identifier as server S1, S2, and S3. You would pass these domain identifiers to the hash function and get the hash value out. Now, to make sure that the hash value is between the hash space that we have, that is falls between 2 to the power 32, we would mod that output of hash function with 2 to the power 32. Now we get the exact index now, right? Now, this is where the servers are placed on around this ring. Now, this is where things get spicy. When a key needs to be stored, you just have to again find the hash value of that key with the same hash function and go clockwise in the direction of the key's index that you found it right now. The first server that comes in your way is the place where you would store or retrieve that key for. Now imagine, let's say you have a key whose value, hashed value, comes out to be 232, right? Now this 232 key has to be stored in the server that comes next in the clockwise direction. That means server 2 for now. So that's how you keep saving all the keys that comes into the system. Now the very important question is what happens when you add another server, right? That's when we drop the modulus function altogether, right? Okay. Now let's say you have another server called server 4 and the hash value gives you an index which is close to this 1000. Let's say this is where server 4 would fit in. So now at this particular time, only keys that falls between 400 to 1000 will have to be remapped to this server. Any key that is beyond this 1000 up till this value still stays with server 3, and other values which are falling from this range to this range still stays with server 1. So you have achieved a minimal level of your reassignment and no cache doomed stay. Some magic happens when server goes down, right? The keys just move to the next server in the ring. So for example, if this server 3 goes down, all the keys that were assigned to server 3, that is starting from this 1000 till this value, are again remapped to server 1 and no other server in the system has to be impacted. This is magical, right? You don't have to do a lot of reassignment of every key in the system now. But wait, you probably think, what if a server aren't spaced evenly? Won't some server get overloaded? That's correct. And I had panicked moment too. But there is a clever trick for that as well. So let's talk about the virtual node in a few seconds. So Actually, before I had this question in my mind that what will happen when we have hotspots, I was very happy because I have nailed the hash ring. I have achieved minimum reshuffling, and I was very happy. But when I had this thought that what will happen when there are hotspots, because the servers will never be evenly spaced, right? And you will never expect that the keys can be spaced evenly, right? What will happen? Because one server getting a maximum load is again turning to a point where single point of failure will happen for maximum amount of keys on that server, right? So that's when I started understanding about the virtual node concept. So here's the trick. What if I give each of these server multiple identities? For example, if I have three servers with me, and I say that each server will be given three identities or maybe five identities for argument's sake. So that makes my three servers will give me 9 to 15 points on the ring, right? So each virtual node still points to some actual server, but with a spread that is smoother and your risk of creating hotspot is reduced. Now, I know you are thinking about how do we create those virtual nodes. It's as simple as giving these virtual servers some arbitrary name, right? So, for instance, let's say I have three servers, node 1, node 0, and node 2, right? Now, what if I give them three names starting with nodes 0 hash 1, node 0 hash 2, node 0 hash 3? Same with node 1, I give hash 1, hash 2, hash 3. Now, for simplicity, I have reduced the hash ring size from 2 to the power 32 to 1024 so that it's easy to take the numbers and point the number, map the numbers on the hash ring right now for this example. So, now when we have these 9 points that we have to map, we have mapped them on this hash ring, right? That gives me an even distribution of my virtual servers where my keys will be evenly distributed now. This is simple, right? No extra infra, no extra math required. Now, you and me both know that servers are not immortal. They are born to get failed, right? So any good engineer will not design for a system to success. They will design the system for failures. So now we talk about replication. How would we replicate data into the hash ring or into the cache server so that in case of failures, we still serve the request with zero failures? Now, before we move forward and understand replication, let's take a step back and understand what all we have achieved till now. And I trust me, if you have reached till this point, you already are a winner because you understand how you can design a scalable system, right? So till now, we are able to achieve a hash ring mechanism for distributing my caching keys, right? Where we reduce the number of remapping whenever there is a server addition or deletion, right? We were also able to achieve a even distribution, a fair even distribution using the virtual node mechanism. So now comes the last point where we think about how do we safeguard ourselves from server crashes. If in case, let's say, a actual physical server node 2 over here dies, what will happen to the data that was stored on node 2, right? Enters the replication strategies. Now, again, the hash ring is a very sophisticated design where you don't have to worry about replication too much. You just utilize the hash ring itself to unlock this potential for replication as well. Now, imagine that if you want two replicas for your data to be stored, what will you do? Let's say that you want to store a key that is falling around at index 300, right? So ideally, any key that is at index 300 will fall on node 1. hash 1, right? What do we do? If we want to achieve two replicas, we move this key to the next server on the ring. So now this key is stored to two servers. That makes two replicas. Now, if node 1 dies, so wherever we have node 1, this all is gone, right? Altogether. Still, if there is a request to get the key that belongs to index 300, we still have a place to fall back. We still are able to serve the data from node 0 now. That means your system still is able to serve the request. That is the beauty of hashing. Okay, congratulations. You have achieved a scalable system where you have minimum number of remappings, you have evenly distributed data within the server nodes, and you have also made your system resilient. Now, there is a very important question that I have in my mind, and I want you champions to answer that in the comment section below. What if, after achieving all this in the consistent hashing, I want to add or remove a server? What should be my strategy over here? How will the keys be mapped and system still behaves in the way that we want? It doesn't has to fail. Can that happen with the consistent hashing at this particular stage? Let's see if you guys can answer this important question by now. Now, before your brain goes into the full hash overload, let's do a quick recap. So I started with a classic modulus function and felt very smart until I broke the server by adding a new server, right? Then we learned about the hash function, right? With hash functions in place, we use the hash functions with the hash ring to turn the chaos into order. With the hash ring in place, we again introduce a concept called virtual nodes, which helped us evenly distribute the keys into multiple servers. And to be resilient, we again discussed on the replication mechanism. So now we can scale a system without panics, without pain, and definitely without breaking the production at 2 a.m., right? So now theory is enough, right? But let's be honest. I know you want to see some code, right? So in the next video, I'll show you how to implement consistent hashing in Go, completed with virtual node, data mapping, and replication like a boss. So make sure you subscribe to this YouTube channel so that you don't miss out that video where we are implementing the consistent hashing in Golang. Also, make sure that you share this video with your fellow colleagues who want to understand consistent hashing in depth.